This is Dr. Kayla Kaiser from the California State University at Northridge. I'm going to tell you about stoichiometry today. For all these calculations, I'm just going to be using three significant figures. In this first question, we have molecules of oxygen is what we're looking for, and grams of sulfur is what we're given. So we start by converting grams to moles. That's the first step in any stoichiometry problem. Then we use the mole ratio from the balanced chemical equation, the coefficients, and we arrive at molecules of oxygen using Avogadro's number. We have to decide where we're going to start with this problem, and we're going to start with the number given, that's 16 grams of sulfur. We're deciding where we want to go, and it says in the problem molecules of oxygen. The next step is to go from grams to moles using the molar mass of sulfur. Then we use the coefficients from the balanced chemical equation in a mole ratio. That's 2 moles of sulfur consumed for every 3 moles of oxygen consumed. Finally, we use Avogadro's number to get molecules of oxygen in 1 mole of oxygen. The answer that we get is very large. It makes sense because oxygen is a small molecule and it requires a lot of molecules for 1 mole. In question 2, we are given 7 grams of nitrogen, and we're asked to determine the number of molecules of hydrogen needed to fully react. We're going to go from grams to moles using the molar mass of diatomic nitrogen, so we have to calculate that. Then we're going to use a mole ratio based on the chemical equation. And finally, we're going to use Avogadro's number to get from moles to molecules. In this problem, we have to decide where we're going to start, and that is with the number given in the problem, 7 grams of nitrogen. That's the number, the unit, and the substance. We're going to use the molar mass to get to moles. That is the best way to do any stoichiometry problem. Then we're going to use a mole ratio to get from moles of nitrogen. 1 mole of nitrogen requires 3 moles of hydrogen. And finally, we're going to use Avogadro's number to get from moles to molecules, just like we did in the previous problem. Again, we get a very large number, and that makes sense because molecules are very small. For the third question, we're going to determine the number of grams of oxygen produced by decomposition of hydrogen peroxide. So we have to start with the 41 grams of hydrogen peroxide, calculate the molar mass of hydrogen peroxide to get to moles. Then we're going to use a mole ratio from the balanced chemical equation to get to moles of oxygen that's produced, and then we're going to calculate the molar mass of oxygen gas to get from moles of oxygen to grams of oxygen. If we start with the 41.1 grams of hydrogen peroxide, that's the number given in the problem, and we want to end up in grams of oxygen. Just like any stoichiometry problem, we have to get to moles before we can go from one substance to another. So first we need to use the molar mass of hydrogen peroxide to get to moles. Then we're going to use the mole ratio from the coefficients of the balanced chemical equation. And then last, we're going to use the molar mass of diatomic oxygen. That's 2 oxygen atoms for every 1 mole. And we will arrive at grams of oxygen. The number that we get makes sense because of the stoichiometric ratios in the equation. In this fourth question, we are going from copper to silver. We start out with 49 grams of copper. We have to get to moles using the molar mass of copper. Then we use a mole ratio from the chemical equation to get from copper to silver. And finally, we're going to use the molar mass of silver to get from moles of silver to grams. We have to decide where to begin, and that is with the number, unit, and substance given in the problem. That's 49.1 grams of copper, and we are trying to get 2 grams of silver. To get from grams to moles, we're going to use the molar mass of copper. You get that from the periodic table. Then to get from copper to silver, we're going to use the coefficients of the balanced chemical equation. That's 1 mole of copper for every 2 moles of silver. And then we're going to use the molar mass of silver to get from moles to grams of silver. The answer that we get is larger than what we started with, which might be surprising, but that's okay because that's how the chemical equation works. In the previous problems, we had an excess of one of the two reactants, we are only basing everything on one reactant. But what if something runs out? In this example, we're talking about large objects such as mangoes and loquats. If you have a situation like this and making fruit baskets, you can use a chemical equation to abbreviate the recipe. So we have 2 mangoes and 3 loquats for every fruit basket. In the second example with large objects, say that you work at a bicycle shop. For every 2 wheels, you need 1 frame and 1 handlebar and 1 crankset to make a complete bicycle. Looking at the pictures here, you can see that the theoretical yield of these parts inventory are 4 bicycles. We've run out of wheels, that's our limiting reactant, and we have an excess of frames, handlebars, and cranksets. In some instances, the reactants might be given in exactly stoichiometric amounts. In this equation, there would be 2 hydrogen molecules for every 1 oxygen molecule, or for 1 mole of hydrogen, you would only need half as much oxygen. In other instances, the reactants might not be given in stoichiometric amounts. When one of the reactants is used first, this is called the limiting reactant. The limiting reactant is in the shortest supply and limits the amount of product that you can make. In this example, you need 2 sulfur atoms for every 3 molecules of oxygen to make 2 molecules of sulfur trioxide. This picture shows that 2 plus 2 does not give us the ratio that we need to make 1 sulfur trioxide molecule. To find the limiting reactant in general, we look for which reactant makes the least amount of product. So here's an example with sulfur dioxide combining with oxygen gas to make sulfur trioxide. Our solution map is to go from moles of reactant to moles of product in both cases and look at which answer is less. So we're going to start with the numbers given in the problem for both of the reactants. We're going to use a mole ratio based on the balanced chemical equation, and we're going to arrive at an answer in terms of moles of product. Then we look at the 2 numbers and decide which one is less, and that's going to tell us that the sulfur dioxide is the limiting reactant. In this combustion reaction, we have propane and oxygen giving us carbon dioxide and water. We're going to start with the amounts of propane and oxygen gas and look at how many moles of carbon dioxide can be made. In this example, we have aluminum hydroxide and hydrochloric acid, and the question is asking how many moles of water will be made. So we're going to start with the moles of each reactant and go to moles of product. You see that the amount of product that's made from each reactant is the same. That means that these are given in a stoichiometric amount, and there is no limiting reactant in this example. So let's do another question. If we are reacting chlorine gas with sodium hydroxide and we want to know how much water we can make, but we have excess chlorine gas, we can ignore the chlorine and start with the kilograms of sodium hydroxide. We have to use a metric prefix equivalence to get to grams. Then we can use the molar mass of sodium hydroxide to get to moles of sodium hydroxide. And finally, we can use a mole ratio to get from moles of sodium hydroxide to moles of water. So we decide where we're starting, that's the number given in the problem, and we define where we want to end up. Then we're going to use our metric prefix. There are 1,000 grams in 1 kilogram. Then we're going to use grams to moles, that's the molar mass of sodium hydroxide. And finally, we're going to use a mole ratio from the balanced chemical equation. For every 6 moles of sodium hydroxide, we're going to be able to make 3 moles of water. And we get a numerical answer, which is very large. And that makes sense because 23 kilograms is a large amount of starting material. In the next question, we have iron oxide reacting with carbon monoxide, and we want to know how much carbon dioxide will be produced. Luckily, it tells us in the problem that the iron oxide is in excess, so we don't have to worry about that. We're just going to focus on the reactant that's given a certain quantity, that's the 234 grams of carbon monoxide. We're going to use a mole ratio to get to carbon dioxide, and then we're going to use the molar mass of carbon dioxide to get to grams. So we're going to start with the number given in the problem, that's 234 grams of carbon monoxide. First, we're going to go from grams of carbon monoxide to moles of carbon monoxide using the molar mass. Then we're going to use a mole ratio and the molar mass of product, that's carbon dioxide. We get an answer that's a large number of grams of carbon dioxide, and that makes sense because we started with a lot of starting material. In question 7, we're reacting a certain quantity of sulfur with a certain quantity of oxygen. Since we don't know which is the limiting reactant, we have to go through the whole process for each reactant to determine which will run out first. So we'll start with sulfur, we'll go to moles, and then we'll go to moles of product. Then we'll start with oxygen. We'll go through moles of oxygen and go to moles of product. Then we look at which one is less, and that's going to lead us to our answer. In this case, we have two starting points. We're going to start out with the 6.3 grams of sulfur and the 10.0 grams of oxygen. In both cases, we're trying to get to moles of product. We're going to use the molar mass of sulfur and the molar mass of diatomic oxygen, and then we're going to use a mole ratio based on the stoichiometric coefficients in the balanced chemical equation. If we crunch this in our calculator, we're going to arrive at a numerical answer for each starting point. Then we look at which one of these answers is less, and that's going to indicate to us that sulfur is the limiting reactant because it's going to make fewer moles of product. In this next example, we're starting with a certain quantity of chlorine gas and a certain quantity of sodium hydroxide. Again, since the quantities of two reactants are given, we're going to have two starting points to determine which is the limiting reactant. Since no desired product is specified, we can choose anything in the product side, either sodium chloride, sodium chlorite, or water. So our solution map is going to begin with chlorine. We're going to go to moles using the molar mass, and then we're going to go to moles of product, and I chose sodium chloride just for convenience. Then we're going to start the same way with sodium hydroxide, go to moles of sodium hydroxide and moles of product. Then we're going to see which is less, and that's going to determine which is the limiting reactant. So again, we have two starting points because we have two different reactants and both quantities are given in the problem. We're going to use the molar mass of chlorine and the molar mass of sodium hydroxide to get to moles. Then we're going to use the mole ratio from the coefficients of the balanced chemical equation to get to moles of product. We can get a numerical answer for moles of sodium chloride based on both reactants, and we see which one is less. The sodium hydroxide is going to produce less sodium chloride, so sodium hydroxide is our limiting reactant, and the chlorine gas is in excess. This is our last example. We're going to start with magnesium silicide and react it with oxygen. And since the desired product is not specified, we're starting with the same quantity of each reactant. We can choose either of the products that we like to determine. I'm going to use silicon hydride because the stoichiometric coefficient is 1 there. So we're going to start with grams of magnesium silicide and using its molar mass get to moles, then using a mole ratio get to moles of product. Then we're going to take grams of water, go to moles using molar mass, and get to moles of product, the same product. Then we're going to see which is less, and that's going to tell us which reactant is limiting and which reactant is in excess. Since no substance is given in the problem, we have to apply the 50 grams to each of our starting materials, the magnesium silicide and the water. We're going to get to moles of each of our reactants using their respective molar masses, and then we're going to use the mole ratios that are given by the stoichiometric coefficients in the balanced chemical equation to arrive at moles of product. And again, I just chose silicon hydride as the convenient product to go to because its stoichiometric coefficient is 1. We look at our two numerical answers and we ask which one is less. The 0.652 moles of silicon hydride is our theoretical yield, and we can determine that magnesium silicide is the limiting reactant and water is in excess. So just to summarize, if you're given the quantity of a reactant and the problem states the other reactant is in excess, then just do the calculation based on one of the reactants. It's really helpful if you specify your starting and ending points. If you're given the quantities of two or more reactants, you have to determine which is the limiting reactant. You want to go through moles no matter what. And it's very easy to see which is the limiting reactant. That is the reactant which produces the least amount of product.